All right, so here we have a rather difficult question that involves some significant amount of calculus, Newton's laws, both rotation and translation, and just kind of a really sort of difficult to grasp description of what's happening. If you see a problem like this on the actual AP test, you are welcome to spend about 30 seconds crying before you actually attempt it, because it's going to be quite hard. But the good part is it'll be hard for everybody. So the better you can get pieces of it, the better you'll do. So focus on that. Okay, so part A, and the good part is, in this question at least, it gives you a lot of hints. So we are going to start, it says start from Newton's second law in either translational or rotational form. So I'm just going to write that down. Right? That's what we're starting from, somewhere along the line. And since A part 1 is a linear velocity, I'm going to probably be using this one for A1. And part B is an angular velocity, so I'm probably going to be using this for A2, right? And that gives us a basis for what's going to happen, right? Before I even looked at the question, I know that I've got F equals ma, and it's going to help us figure out the linear velocity. And I got tau equals I alpha, it's going to help us figure out the angular velocity. So let's look at the actual problem. We have something that's sliding, so it's not rolling at all. And it hits friction, and so the frictional force provides a torque that causes it to start rotating. But it also provides a net force in the backwards direction, so it slows it down, right? So the friction both provides the torque that makes it rotate and provides a force that slows the object's forward velocity down as well, right? It has a negative acceleration for that period of time. So let's start with the A part 1, the linear velocity, and go from there. So for this one, we have our object on the ground. Well, actually, I don't even need the ground for this one. And it's moving with speed v, and it hits the friction surface. And since this is not a rotation question, I'm just going to draw the friction force, right, like that. It doesn't matter, and we know it is applied at the point of contact, but for this, where it's applied doesn't matter. So the net force is just the frictional force. And we also have a weight and a normal force, right, that are perfectly balanced. So the net force is the friction force, which is mu times n, and n is the weight, mg. So the friction force is mu mg from the free body diagram. And now we're going to use Newton's laws. So mu mg in a negative, because it's in the negative direction, equals ma. So we'll cancel the masses. And we get negative ug equals a. And now, right, the key is differential equation. So the only thing here that we could potentially write as a differential thing is the acceleration. So negative mu g equals dv dt. And that is A part 1. Right? That's all I've done. Set it up. I drew a free body diagram just because it's kind of a complicated description. It doesn't really change the process, right? Find the net force, write F equals ma, and then rewrite the acceleration as the derivative. That's what gets you to the differential equation form. So that's A part 1. A part 2. So now, only a couple things change. So now we need to be a little bit more careful with the friction force. It's still the only force, right? We have a normal force, and we have a weight. So it's still the only force that causes acceleration, but we have to be a bit more careful about where it's applied, right? Which is at the point of contact, right? So we also have the radius r. I guess a capital R in this problem. It's for consistency. Okay, so the torque is, the normal force doesn't apply at torque because you got the sine of 0 degrees. The weight doesn't apply at torque because it acts at the center of mass. But the frictional force does. So the net torque is just due to friction. And so I'm going to call it tau sub f is Fr. And then the sine of theta would be sine of 90 degrees, or 1. And once again, the friction force is mu mg, so this is mu mg. Oops. And we're also told that this thing has, it's a ring, so we know it's a moment of inertia. So let's substitute all this in. So mu mgr equals mr squared alpha. Right? And you notice that I've kept the torque positive here, even though it's sort of in the backwards direction, because this torque would cause the hoop to start rotating in a counterclockwise or positive direction. So I don't have a negative sign in this one. So we can cancel some things. We cancel one mass and one r. And so we're going to divide by r. We're going to get mu g over r equals alpha. And once again, we know we have a differential equation. So we can rewrite mu g over r is d omega dt. And that is a part 2. And so if you can do that and nothing else on this problem, you've gotten the 6 of 15 points, which is pace for basically a 3 or a 4. And this is the hardest question, I think, that I can find. So setup is important. Right? We're not being asked to solve this equation yet, but free body diagrams, Newton's laws, this is something all of you can do. Okay. So now we're going to move to part B. For part B, we have to actually solve these differential equations. Right. And the tricky part of this, as we'll see, is going to be the ends of the integral. So we have our result for the linear velocity. We had dv dt is negative mu g. And so this equation is one that can be solved with separation of variables. So I'm going to do that. dv, right? And now we have to integrate both sides. Actually, I'm going to write this a little bit nicer. Okay. So our velocity integral. So what velocity do we start at? That's what goes down here. And then what velocity do we end at is what goes up there. So the velocity we start at, we're told, that's v0, right? We're moving with some velocity v0. That's the first picture on the left. At some time t later, that's our function, right? Our velocity v. In terms of time, our integral is fairly similar. We start at t equals 0, and we end at some time later t, right? So these things are sort of paired up. At t equals 0, we're traveling v0. At time t, we have velocity v. So one side of the integral is quite easy, right? We just have v evaluated at v and v naught, so v minus v naught. And the other side is also quite easy. The mu and the g are constants, and so we're evaluating t from 0 to t, which is just t. And so v, as a function of time, is just v naught minus mu g t, right? And that's it. And that makes, hopefully, conceptual sense. Our velocity starts with v0 and then gets smaller. Our velocity starts at v0 and then it gets smaller, which makes sense. Friction is opposite the direction we're moving in, so it slows us down. Good. Okay. Now, same idea for the other one. We have d omega dt is mu, that was sloppy, mu g over r. Same thing. This could be solved with separation of variables, so we will separate and with the variable separated, we again have to integrate, but the ends of the integral are just a little bit different because the conditions are just a little bit different. So omega, before it hits this surface with friction, it's not rotating at all. So we have 0 angular velocity initially, and at some time later it's that function omega that we're solving for. And so again, we're still integrating from 0 to some time t, and so once again these are sort of paired up. So our left side is straightforward, it's just omega, and our right side is the same sort of thing, right? Mu g r t. So omega right, is this function. Okay. So the key, right, again, the key to this question is being careful with these ends of the integral, right, the velocities and the angular velocities. Because if you can describe how your velocity and angular velocity start, you can then solve the rest of the problem. That's where the real challenge is. Separation of variables integration is not too hard because these integrals are obviously very easy to do once you know the ends. But if you can just, if you separate variables correctly and get the endpoints right, that's the point, and then actually doing the math is the other point. So this one's, right, A and B parts 1 and 2 is another 4 points. Okay. So now we need to start putting things together. And this part, those parts are tricky, but they're sort of computationally tricky. Part C is a very, very important reasoning statement. So we have to ask ourselves, what is true when we sort of stop slipping? We're at the rolling with no slipping condition. And that's this condition, oops, I'm going to go back to my typical color. So the condition that rolling, we're no longer slipping, is the condition that V equals R omega. That must be true. And so we have functions, we have this as a function of time, and this is a function of time. So we want to figure out what time this relationship happens at. So we can go back and look at our answer. We get V minus V, oops, sorry. So V equals V naught minus mu gt, and that must equal, at some time t, r times mu gt over r. Right? So we can cancel those r's. And so we get V naught equals 2 mu gt, or t equals V naught over 2 mu g, right? And so this statement is that much time must pass until that rolling without slipping constraint is satisfied. Basically, until friction has had enough time to make the wheel spin enough such that its rolling motion is connected to its translation motion, and it matches the description of rolling without slipping that we've used before. Okay? So that's tough. Like, the math on that is easy once you recognize that this is the statement that you're evaluating. But recognizing that is exceedingly hard, I think. So this is something to sort of be aware of. Remember, what rolling without slipping means. It means that equation must be true. Okay. So the next thing is we have a time, and we want to know how fast we're traveling. Well, we know V equals V naught minus mu gt, V naught minus mu g, and we just found t, V naught over 2 mu g. So we can cancel the mu g's, so V naught minus V naught over 2, so V naught over 2. Right, this one, I think, if you get the time right, is fairly straightforward. And again, if you get the time wrong here, whatever you get there, just plug it into this, right? Your goal is to find your velocity at that time, and so that's just plug and chug. Right? You have to recognize that that's what you're doing. If you get the time wrong, fine, but plug it into your velocity function, whatever that was from before. All right? And finally, part E. How far do you travel? Well, we have v of t, and we want delta x in some sense. So that's an integral. So if we L, or delta x, I'll just leave the delta x. So now L, which is what we're calling delta x, is the integral of v of t dt. And the time it takes, we found, right? We start at t equals 0, and we end at the time we calculated in part C. That's how long it takes us to travel the distance L. That's v naught over 2 mu g. It's kind of an ugly end to the integral, but that's fine. So now we can plug in. So v of t is v naught minus mu gt dt. So the first term is easy to integrate because it's a constant. So L equals v naught t. The second term is pretty easy to integrate because it's linear. Right, and then we evaluate this at 0 and v naught over, oops. Right, so when t equals 0, we're going to see we're just going to get 0. So all we care about is right, this endpoint. So we plug that in. So v naught over 2 mu g minus mu g v naught over 2 mu g squared over 2. Now we just need to simplify. V naught squared over 2 mu g minus v naught squared over, so we cancel one of those factors of mu g. So we have 1 over 2 squared divided by 2, which is 8, and we're left with one factor of mu g. So if we're to find a common denominator here, right, this would be 8, that would be 4. And so we'll get L equals 3 v naught squared over 8 mu g is how far you travel before you start rolling without slipping. Okay, so again, this question is very hard, especially parts C, D, and E. But if you can do parts A, where it tells you where to start, and it's just to set up an equation, you can get 6 out of 15 points here. Everything else is, I think, sort of a bonus on this question. If you can do it, great. It's a great challenge question. But you have to be able to do part A. The setup, the organization, sort of knowing how to manipulate Newton's laws using free body diagrams. Okay? So make that your goal. Make sure you can understand part A, and everything else, make sure you can kind of not be completely lost on. You can go maybe get a point or two here and there, and you get 8 out of 15. That's a pace for a 5.